So we're doing a planned comparison off of the ANOVA that we did last time. For planned comparisons, you're really limited to the number of groups that you have, -1, because whenever you have a family of hypotheses, that's called the family of hypotheses, each hypothesis has its own type 1 error, and that's called the per comparison error rate. If you put all of the type 1 errors together, that's called your family-wise error rate. So basically, the whole assumption is that if you have an alpha level of 0.05, that means that 5 times out of 100, we could get significance due to chance alone. That's our type 1 error rate. So if we have a bunch of comparisons that we try to do, chances are we could get significance, even if we don't really have it. So number of planned comparisons that we can do, and by planned I mean you're doing it before you've seen the data, is limited to your number of groups -1. So here it would be 2. Before you have to start correcting for type 1 error. So to do planned comparisons, say for example, we could compare any of these, but we're limited to 2, right? So we could compare A1 to A2, or we could do A1 to A3, or we could do A2 to A3. So just as an example, I'm going to do A1 to A2, and I'm going to do A1 to A3. Okay, so to start off with a comparison, we need to assign coefficients. Coefficients are just an arbitrary way of mathematically calculating it. So say, for example, if I'm doing A1 versus A2, all my coefficients need to add up to 0. So for my first comparison, I'm going to assign A1, 1, A2, -1, and A3, 0. And what this means is that I'm comparing A1 to A2, and 1 plus -1 is 0. So these coefficients, like I said, are arbitrary. You could also do +1/2, -1/2, 0. It's however you want to assign them to equal to 0. And I'm actually going to put these coefficients into my equations to figure out the sum squared for these single degree freedom comparisons, also called psi comparisons. So I'm going to use whole numbers because that's easier to do. And again, if you're looking A1, A2, and A3, that just tells me that I'm comparing A1 to A2. So I have specific equations that the book gives you. The first one that you need to know is sum squared. Psi is the little notation that we use for the single degree of freedom comparisons. N is equal to the number of subjects per group. Psi is what we're going to find, and this is the sum of all of our coefficients squared. The second formula that we need, since we don't know this number, and this is also from the book, it's just the sum of all of our coefficients multiplied by our means of our groups. So these are the 2 equations that I need, and you can get those from your book. So we're going to do this one first. Psi, that refers to our single degree of freedom comparison. We're going to do the sum of all the coefficients times the means of the groups that we're comparing. So my coefficient for A1 is 1, times my mean for group A1, which I calculated to be 3.5. I'm going to add that to my coefficient for A2, which is -1, times my mean for A2, which is 4.75. You would also add the coefficient of A3, which is 0, so we're just going to take that step out. And that's my psi. So that is just a number that we're going to put into this equation to get our sum squared. So here, N is the number of subjects per group. So I've got 4. Psi is from here, so it's -1.25 squared, divided by the sum of all my coefficients squared. So my coefficients, remember, are 1, -1, and 0. So I'm going to have 1 squared plus -1 squared plus 0 squared. And I get a number of 3.125. So I have a sum squared for just this comparison of 3.125. So remember conceptually, again, when we did the overall ANOVA, which is analysis of variance, we realized that there was a significant difference, but we don't know where that difference is. We just know there's a difference somewhere between these groups. So the reason why we're going in and actually comparing to these groups is to pinpoint exactly where that difference is. So eventually I'm going to put this back into another source table that looks exactly like the one that you did in ANOVA for all these comparisons. So for our second comparison, and this is just an example, I'm going to do A1 versus A3, which means I'm trying to see if the significant difference that we got from our overall ANOVA came from the differences between A1 and A3. So I'm leaving out A2. So I'm going to do coefficients of 1, 0, minus 1. And again, these are arbitrary numbers. You could also do plus 1/2, 0, minus 1/2, just as long as these add up to 0. So I'm going to plug the same numbers into my equations up here. So again, that is the sum of all my coefficients times the means of each of my groups. So coefficient for A1 times the mean of A1 is 3.5. And I could leave out group 2 because my coefficient there is 0. And then my coefficient for A3 is minus 1. Okay, thanks. And my mean for A3 is 6. So when I calculate that out, I'm going to get 2.5 minus? Yep. Okay. I'm going to put this number, which is my psi, turn back into here to get my sum squared for this one. So n, again, is the number of subjects per group, which is 4. My psi is minus 2.5, and I'm going to square that. And then this is the sum of all my coefficients squared. Right? So I've got 1 squared plus 0 squared plus minus 1 squared. Since these are also called single degree of freedom comparisons, your degrees of freedom here are always going to be 1. The reason for that is that we're only comparing 2 groups at a time, right? Even if you tried to composite them and said A1 and A2 versus A3, you would still be putting 2 groups compared to each other. If you try to compare more than 2 groups at a time, you would have to use completely different equations. So my degrees of freedom for my single degree of freedom comparisons is always 1. Mean squared, which is our true variance estimate, it's also the error term, is going to be sum squared divided by degrees of freedom. So it's just going to be the same because I'm dividing by 1. To get my F values, it's just going to be my mean squared divided by my mean squared of the within term, right? This is also called my error term. The reason for that is that in ANOVA, we're basically looking to see if there's a difference between 2 groups. So we want all the variance to be between the groups. If we have a lot of variance within one group, it's going to be very difficult to show that 2 groups are different. So the within variance is also called the error because that's going to be something that's happening that's not attributed to our treatment.
This is also called my error term. The reason for that is that in ANOVA, we're basically looking to see if there's a difference between 2 groups. So we want all the variance to be between the groups. If we have a lot of variance within one group, it's going to be very difficult to show that 2 groups are different. So the within variance is also called the error because that's going to be something that's happening that's not attributed to our treatment.
So here, my F value is going to be 3.125 divided by 1.08. And here, it's going to be 12.5 divided by 1.08. So these are my F values. Again, if your comparisons are orthogonal, which means that they are independent and non-overlapping, then the sum squared of all of your individual comparisons added should equal your between sum squared. Here, our comparisons are not completely independent and non-overlapping because I used A1 twice. So from these F tables, we're going to do the exact same thing that you do in ANOVA. So you're going to take your degrees of freedom, And we're probably going to do it in a 0.05 alpha level because that's what we like. So degrees of freedom is going to be 1, and your within term, 9. You're going to look that up in the back of the book, and you're going to get a critical value of 5.12. So this is our F critical value. Critical always refers to you get it from a table, and it's 5.12. Now remember, our obtained F values, which is also our F calculated values, always need to exceed this number. An easy way of remembering is that you did all this work to get these numbers, so you just want them to be bigger, whereas this number you're just getting from a table. So since this number is not larger than an F critical, this one is not significant at the 0.05 value. However, 11 is larger than 5, so this one is going to be significant at the 0.05 value. That means, since our comparison 2 was A1 versus A3, that our A1 and A3 groups significantly differ at the 0.05 value, but our A1 and A2 groups do not significantly differ. Okay.
Outstanding! Oh my goodness gracious!